Well, good morning. Absorption and air stripping. For those of you that took 489 in the spring, you'll notice some of these slides may look familiar. I recycled some of the slides, added some new slides, because when we talk about absorption, it applies both in water systems and in gas treatment. So in terms of water treatment, where we need to think about absorption is for instance, in aeration systems. So we've talked about oxidation of iron and manganese. So we've talked about, especially with iron, you're looking at the transfer of oxygen from either from the air or from some sort of a mechanical or diffused air system, and you want to inject that into the aqueous stream. We also talked about aeration systems for wastewater treatment. So we talked about activated sludge systems, and I'll show you some pictures of the diffusers. That's critical. We also talk about aeration in terms of post-treatment, so what they refer to as post-aeration. So just before discharge into the receiving body of water, we need to add oxygen in order to aerate and that waste stream so that we don't have or don't cause detrimental impact on the receiving body of water. In terms of disinfection, we talked about dissolution of chlorine gas, actually also same with ozone. So we have some sort of a gas, we need to dissolve that in water, and then it's once we have that gas in the aqueous stream, then disinfection can occur. In terms of water and wastewater treatment, we can also think about transferring chemicals from the liquid stream into the gas stream. So for instance, in groundwater treatment, where you have insoluble organic chemicals such as trichloroethylene, tetrachloroethylene, benzene, toluene, xylene, if we looking at treating that groundwater stream, we can then transfer that chemical from the aqueous stream into the gas stream, and then we can treat it in the gas stream. So that could be treating it, for instance, with catalytic incineration. It could be treating it with an adsorption process. And then we also mentioned with groundwater that if the CO2 level was too high, then remember reaction 1, which was the neutralization of CO2, produces a significant amount of sludge. So if that CO2 level is too high, then what we want to do is we want to strip that CO2 from the aqueous stream before the water flows into the rapid mix basin, followed by flocculation. So all of these result or involve some sort of mass transfer across the air-water interface. And this is the model that I'm showing here. So if we look at this, in this case, it's written with SO2. Okay, so if we have SO2 in one of those mornings, we have SO2, in this case shown in the airstream. We can dissolve that and transfer that from the airstream into the aqueous stream. Once it's in the aqueous stream, it would react with water to form H2SO3. We can think about this in terms of oxygen. So we have oxygen in a gas stream. That oxygen can be transferred across the air-water interface. So we have oxygen in an aqueous stream. So in all cases, what we're looking at is in the transfer across this air-water interface. And the rate of transfer is a function of, sorry, the temperature. We'll write it in terms of oxygen, but the partial pressure of oxygen or the partial pressure of gas, the concentration of the oxygen in the aqueous stream, the mixing efficiency, and the composition of the water. These are among the factors that will affect this rate of transfer. And you can think about it in terms of oxygen. Where would you expect to find a higher concentration of oxygen in a stream? In a stream that is where the water is extremely cold, very cold, or where the water is warm. Those of you that fish, which waters are you more likely to want to fish in? Cold waters or warm waters? Okay, cold. Why? The rate of transfer of oxygen is a function of the difference between the saturation concentration and the actual concentration. And the solubility of oxygen in water is much higher in colder water than it is in warm water. So given the same actual concentration, the driving force is greater in cold water than in warm water. So you're going to see a greater rate of mass transfer. It's going to, okay, so the other thing is mixing efficiency, which, given the same temperature of the water, would you expect to have a higher concentration of oxygen in a stream that is very quiescent? So kind of think about the Red Cedar upstream of the rapids, or in the Red Cedar downstream of the rapids. So where would you expect to have higher concentrations of oxygen in the water? Downstream. Why?
More mixing,
Exactly.
Turbulence.
More turbulence, more mixing. So because you've got more turbulence, more mixing, that increases your transfer efficiency. So in terms of absorption efficiency, or really we can think about this in terms of mass transfer efficiency. In a engineered system, the ratio of the flow rate of the liquid to the gas will affect efficiency, and we'll look a little bit at this. The solubility of the gas plays a significant role, and we talked about this in terms of the effect of temperature on oxygen solubility. So temperature plays a significant role. That contact, and we talked about that in terms of the oxygen level in the Red Cedar upstream of the rapids and downstream. And the other thing is the composition of the water or the wastewater. What you will find, for instance, if we look at any sort of mass transfer unit, the mass transfer efficiencies are actually determined using pure water. It's not determined using wastewater. But what you'll find is that the transfer efficiency decreases when you move from water to wastewater. The efficiency is actually less. We didn't talk about designing aeration systems. I believe that's covered in ENE 804. So for any of you that are either in the BSMS program and will take 804, you'll learn about that there. Or if you plan to go to grad school, you will most likely, if you go to grad school in environmental engineering, you will have a course in biological treatment where it's covered in that course. So just and I've mentioned some of this, but reiterating, we can use air stripping to transfer volatile components from a liquid stream to a gas stream. Again, typically we're looking at, for instance, a groundwater remediation project where you have, for instance, BTEX, trichloroethylene, tetrachloroethylene, and these are chemicals that are sparingly soluble and have a high Henry's constant, law constant. Ammonia is another chemical that can be removed. This is pH dependent. What you're removing is ammonia, not the ammonium ion. So the pKa is about 9. So you'd have to, if you're looking at removing ammonia by air stripping, you would have to increase the pH above 9 so that the ammonia is in the form of ammonia, not ammonium ion, and then could strip the ammonia. Typically with these types of systems, they're more effective at warmer temperatures. That's not true for oxygen, but it is true for removing these volatile components, for instance, from a liquid stream, so from groundwater. There are a number of types of units we can use. We can use spray towers. So spray towers have no internal components except these spray nozzles and the connecting piping. These can be used for volatile gases, for instance, hydrogen sulfide, vinyl chloride. It can be used for CO2 stripping from a groundwater before lime soda ash softening. Notice these are typically a countercurrent system. So you have air flowing from the bottom, air flows up, your liquid stream flows down. And these are useful. They have very low pressure drops. So for very volatile chemicals, they then can be used. Spray towers are useful for chemicals that are not quite as volatile as vinyl chloride or hydrogen sulfide. They provide good contact, and what you have are these trays here, and the water flows again, typically from the bottom up and out the top. Water typically flows downward. So you're pumping water up and then allowing it to flow down. These are reliable. They're used for CO2 stripping in groundwater systems. They can be used for removal of chlorinated solvents from groundwater. They can be used for BTEX removal, etc. Okay. The equation, I gave you the equation here. It's actually provided in the FE handbook. And it just simply says that the concentration leaving, so your concentration in your water leaving, so this would be Cn, so N is the number of trays, is equal to C0 10 to the minus K, which is a coefficient provided by the manufacturer, typically ranges from about 0.12 to 0.16 for CO2. It's specific to the contaminant. And then times the number of trays. So this can also be used to determine the number of trays that are needed for a tray tower. When these are used for gas treatment, they're typically referred to as scrubbers. That term is typically not used in water treatment or wastewater treatment, but it is common in gas treatment. And in part, that's because when we're looking at gas treatment, you're also achieving some particulate removal. That's not the case in water treatment. These are packed columns. Packed columns are more efficient than either the spray tower or a tray tower. They use these type of packing materials that you see here to provide really a good surface contact, surface area. They typically can achieve 99% removal of volatile organic chemicals. Height is typically about 5 to 12 meters. So they're quite tall. When they're that tall, they tend to be permanent, or they can be mounted on mobile units. And again, typically you have a countercurrent flow with the liquid. You can see the liquid here. So the liquid flows down and your gas stream. Now, for wastewater treatment, we typically used a diffused aeration system. So it would be what you would see in an empty aeration basin. So for activated sludge. And what you can see is you have this grid of, in this case, these are membrane type diffuser. These are fine diffusers, and your oxygen flows, is pumped through this piping and then into the water. These are coarse diffusers, so these are larger diffuser, and again, your oxygen is flowing from the piping network into the water. You can see that a significant amount of money is spent on these diffusers in order to try and get as much of that oxygen into the water. It costs money to produce the oxygen stream. So you want to make sure that you're using it as effectively as possible. You can also use mechanical aerators. These are shown in ponds. These can be used in lagoons for treatment. You're using some sort of mechanical aeration in order to impart or add that oxygen into the water. These are cascade aerators. The one on the left is actually a photo that Craig Tatara had sent from the Genoa Osceola plant. And you can see the water's just cascading down this stream. And as it does, it's adding oxygen. And there's another picture on the right. Any questions about any of these types of systems that we use to transfer either a chemical from the water to an airstream or from the airstream to the water? So looking at this process of mass transfer, what we have in all cases is we're looking at having, in this case, it's shown here with a chemical in the bulk gas phase. This could be oxygen. We need to transfer that chemical to the air-water interface. Typically, we would have a stagnant gas film on the gas side. It has to cross this interface. We have a stagnant water film that's actually thicker, quite a bit thicker than the gas film. And then it has to move out into the bulk liquid. So we have diffusion of the chemical to the surface. We have transfer across the air-water interface. And then we have diffusion away from the liquid. Or it can be the opposite, in which case it's diffusion from within the gas phase, within the liquid phase, and then mass transfer across, and then diffusion from the gas phase. If we can mix this, we can increase the rate at which that chemical then approaches the interface. Now, the design, all of our design is based on Fick's law, which describes this mass transfer across the air-water interface, and Henry's law, which describes the relationship between the concentrations in the air and the water phases at equilibrium. So the rate is a function of the mass transfer efficiency times the difference between the concentration in the air and the concentration at saturation. Okay. Or we can write it in terms of the water. And this tells us whether diffusion is from the gas or the water interface. So, for instance, if we're looking here and we're looking at oxygen, so let's look at the situation. If we have, let's say, C star is equal to 10 milligrams per liter, and C water is equal to 7 milligrams per liter, which direction is mass transfer? From the gas to the water or the water to the gas? It's from the gas to the water. Okay. Now, let's think about this. Same thing. So the equilibrium concentration is 10, or saturation concentration is 10 milligrams per liter. And the concentration is, it's oxygen. Think about this. Have you ever turned on a faucet and you fill up a glass of water and the water is cloudy, but you let the glass of water sit and it becomes clear? Anybody ever observed that? At least one. What's happening? Two, why is that water cloudy when it comes out of the faucet?
Is it oversaturated?
Exactly. It's oversaturated with oxygen. So what's happening? Why is it becoming clear?
Some of that oxygen is leaving the water.
Exactly. The oxygen's being transferred from the water to the air, and it becomes clear. So what you're actually seeing are very fine oxygen bubbles, and that's why it's clear. It's nothing dangerous about it. It's just oversaturated with oxygen. So in this case, the transfer is going to be where I've shown here. This is your cloudy glass of water. The transfer is from the water to the air. So that difference tells you whether it transfers from the air to the water or from the water to the air. We model this in a column using the same approach that we've used all semester. We will assume that the mass in is equal to the mass out. So if we're looking at any chemical, it doesn't matter whether it's oxygen, whether it's BTEX, benzene, toluene, xylene, ethylbenzene, whatever. Okay. So the mass, we have mass in the water. We have mass in from the air. Notice I've drawn this as a countercurrent system. And then we have mass out in the water and mass out in the air. And we can write a mass balance as we've done here. Now we'll make some assumptions. We're going to assume that within a small volume, it's delta Z, my solution is completely mixed. So within that very small incremental volume, we have complete mixing. We'll assume we have dilute solution so that we can use Henry's law, which simply states that the partial pressure of a gas is equal to Henry's constant times the concentration in the aqueous system. This is at equilibrium. Be careful with Henry's law. It can be written in this way. It can also be written with the inverse. So in this case, it's PG over the aqueous equals the Henry's constant. It can be written as the inverse. So you really need to know what your units are on for your Henry's constant. We'll also assume that we have no changes in the volume of the air and the water. So the transfer of these chemicals don't change the volumes. We'll assume we have no accumulation in the reactor, and we have no reaction. And because we have no change in volume, then our flow rates are also constant. And we can assume that flow in water equals flow out. Same for. So again, this is just another example showing what we're looking at. We're looking at the transfer of a chemical across this air-water interface. And I'm going to skip over this because I've done the example problems that I was going to do here. So for the transfer, in this case, this is written for the transfer from water to air. In 489, we'll look at the equations for the transfer from gas to water, but in this case, I'm only going to give you the equation for the transfer water to air. So the packing height is Z, and this is for a packed tower. And this is the same equation we used for adsorption, so AD. So we have the height of the transfer unit and the number of transfer units. Definitions are identical to what we used previously. So the number of transfer units in this case, and this is the equation that's provided on the FE exam, is equal to the stripping factor. And notice your stripping factor is equal to a dimensionless Henry's constant. So that's your Henry's constant in this R is atmospheres, liters, moles, degree Kelvin. We're going to multiply that by K, so K cancels. So then this is atmospheres per molar. What that tells me is, so that's my H. That's equal to the partial pressure in the gas phase divided by the concentration at equilibrium in the aqueous phase. So this is the Henry's constant we need, and we need the Henry's constant in units of atmospheres per molar units. So that's what we will use here for H. Those of you that are in 481, I know you've talked about Henry's constant. I'm not sure what units you've used for Henry's constant, but in this case, those are the units that you need for your Henry's constant for this equation. So for a given, if we have a given ratio of air flow rate to our water flow rate, so let's just say this is given. What this tells you, okay, is that the greater the Henry's constant, the greater your stripping factor. So for chemicals that have a high Henry's constant, which means they want to be, they're volatile, they want to be in the gas phase, stripping factor is increased. Okay. Cn is the concentration in the influent water. C out is the effluent concentration, and the height of the transfer unit is equal to your liquid loading rate. Notice in this case, it's in kilomoles per second. So it's the liquid, kilomoles of liquid. In this case, it's water per second per meter squared. And that's the cross-sectional area of your column divided by the molar density of water times the mass transfer efficient rate constant, or the mass transfer constant for that particular packing material. So this comes from the manufacturer. So we'll do this problem here where we're asked to determine the height of a pack tower. We want to reduce the concentration of CO2 from 60 milligrams per liter to 10 milligrams per liter. Anybody remember where that 10 came from? Way back ages ago at Naseum, when we talked about lime soda ash softening, we said that if the concentration of CO2 was greater than 10 milligrams per liter, that you would need to be adding a significant amount of lime in order to neutralize that CO2, producing an excessive amount of sludge. So that was the cutoff, that if the CO2 level was greater than 10 milligrams per liter, that's when you want to consider using a pack tower system. The operating temperature is 20 degrees C. We have an operating pressure of 1 atmosphere. We have a dimensionless Henry's constant. The air-water ratio, flow rate, volumetric flow rate is 160 to 1. My liquid loading rate is 0.4 kilomoles of water per second per meter squared. My KLA provided by the manufacturer is 50 inverse hours, and we're going to assume that the incoming air is free of CO2. We know that that's not the case, but the equation that we're using also assumes that we've got Q sub A C air in. We're assuming that this is equal to 0. We're also assuming, because now we're transferring it from the water to air, we will assume that if we're looking at what's leaving, the flow rate leaving in the water is, so that mass of, in this case, CO2 leaving in the water is significantly less than the mass leaving in the air. So that we're assuming that we have a significant transfer from the water to the air. So those two assumptions are actually made in deriving this equation here. So CO2 in is equal to 60 milligrams per liter. CO2 out is equal to 10 milligrams per liter. Our dimensionless Henry's constant is 0.8317. Our stripping factor is equal to the dimensionless Henry's constant times the ratio, the volumetric ratio in the air to the volumetric ratio in the water. And that is equal to 0.8317 times 160, and that 160 was given, and that equals to 133. So the number of transfer units is equal to 133 divided by 133 minus 1. ln, notice the greater this value is, the closer it is to 1. And this is equal to ln 60 over 10, 133 minus 1 plus 1 over 133. And this is equal to 1.8. So the number of transfer units is 1.8. The height of the transfer unit is equal to L over MW KLA. And that is equal to 0.4 kilomoles per second per meter squared. I apologize for these lines. The lines I've figured out are now a factor of PowerPoint because it doesn't happen when I'm using PDF. The molar density of water, the molar, is 55.6 kilomoles per meter cubed of water. The KLA is 50 inverse hours, and we have 3,600 seconds per hour. So this is equal to 0.52. So Z is equal to 1.8 times 0.52, or 0.93 meters. So it's roughly 3 feet column that we would need. If we were to decrease that concentration, let's say to 5, that's going to increase the number of transfer units. It's not going to change the height of the transfer unit, but it changes the number of transfer units, so that will increase the height. The height of the transfer unit is dependent on my mass transfer coefficient. So we'll end there. So hopefully you understand a little more about absorption or air stripping. You can size an absorption pack tower. And I'll just end with the reminders.